We're now going to discuss some of the key classes in the Project Reactor API. And the reason for doing this is that you'll end up using these classes as you implement assignments that are coming later in this course. So we're going to talk about Flux and ParallelFlux, which are really the most important classes to be aware of. And we're also going to talk about monos, which show up somewhat sparingly in our examples, but are also a key part of Project Reactor. So there are three key classes in the Project Reactor API. The first of them is a mono, and as the name suggests, a mono may or may not emit a single value. That's where mono comes from. There's one. If it completes successfully, it will emit a single value. If it doesn't complete successfully, if it fails, it will not or may not emit a single value. It's similar to a Java completable future or to an async optional. And here's an example that just illustrates how you can take a factor method called from callable, which we'll talk about, and you can take an unreduced big fraction and then reduce it in a background thread using the subscribe on method. And then in that background, you can take that reduced big fraction and convert it to a mixed string, converting an improper fraction to a mixed fraction using map, and then you can use the do on success action operator to print the results. So one return value here can run asynchronously, may or may not return a value depending on various things. Monos, like fluxes, are typically documented using something called a marble diagram. In a marble diagram for a mono, and for a flux for that matter, the timeline flows from left to right. So you can see here, we're starting on the left, going to the right. This is the item that will eventually be emitted by the mono. It's going to be taken as input from the originating mono or the originating source, and then some operator will transform it somehow or another by mapping it or flat mapping it or doing something to it. And the text inside the box indicates what's being done. Again, flat map, map, zip. There's all kinds of things you can do to perform these transformations. And then what we get down at the bottom, the sort of orangish circle, is the result of the transformation that took the green circle and converted it into something else by changing its value. You can even change its type. That's something we'll talk about later. If everything goes well, then the vertical line indicates that the mono completed successfully, and the transformed value is the new value to be pushed up the stream. And if something goes wrong, then there's an X that indicates that something terminated abnormally. There are many, many, many operators on monos. There's ways to make them through factor methods. There's ways to transform them. There's ways to do things that involve debugging or logging, which are called action operators that have side effects. There's concurrency and scheduler operators that can be used to run them in pools of threads. There's ways to combine monos together. There's ways to take the output of a mono and suppress it, so you just know whether it succeeded or failed, but you don't actually get the value. There's operators for blocking, waiting till the computations are done that may be running in the background or a background thread, and so on and so forth. Flux is arguably the most common form of class in the Project Reactor API, and we'll focus a lot on fluxes in this course. So a flux can emit an infinite number of events, which could be 0, could be 10 or 100 or 1,000 or whatever, an infinite number, and it may complete successfully, or it could also fail. It's very similar to an asynchronous Java stream, such as a situation where a completable future is used with a Java stream. Here's an example where we take an emitter that generates big fractions ad nauseum till the cows come home. It'll go on forever. But then we limit it to S max fractions, which may be like 10 or 100 or whatever. And then we go ahead and reduce and multiply each fraction by some constant in parallel using a parallel thread pool that works on computation-intensive tasks. We collect all the results into a list, and then we go ahead and sort and print that list. So that's an example of how you can flow a bunch of different big fractions or events in general together in a flux. Fluxes support backpressure, where subscribers can indicate to a publisher how much data it can consume in one fell swoop. And if you go this route, then after the data has been sent up to the size of the chunk or the tranche, then the subscriber has to request the next chunk or tranche. Fluxes can also be documented using marble diagrams, except they're a little bit more interesting because they have more elements typically. Once again, time flows from left to right. And you have items that are going to be emitted by the flux at some point. There's an operator that indicates what's going to be used to transform the elements that are being emitted by the flux. So again, you can have things like flat map or filter or whatnot. And then the items we see at the bottom are the flux elements that are the result of the transformation performed by the elements in that operator rectangle. If all goes well, then everybody got emitted and we have a vertical bar. But if something goes wrong, if the flux terminates abnormally, then the vertical line is replaced by an X. As before, there are a boatload of operators on fluxes. They're very similar in a lot of ways to the ones on monos, the primary difference being that now there's a stream of these things as opposed to just one of them. And one other thing that's a little different is we typically have a terminal operation like subscribe, which is used to start all the wheels in motion and have the processing be pushed by the publisher or publishers to the subscriber or subscribers. And then the third and final class here is ParallelFlux, which is essentially a subset of the operators defined in a flux that provides a very concise means of processing the elements in the ParallelFlux stream in parallel. And this is quite a bit similar to Java parallel streams. The syntax is a little different, but it's very much the same kind of idea. And you end up with a bunch of elements being pushed through and processed. Now, there are some differences, so it may be more differences than similarities, but it's similar in enough ways that it's worth comparing them. Good luck, however, trying to find a nice description that compares and contrasts parallel streams with parallel fluxes. So to make your life easier, I worked with ChatGPT and got it to give a nice summary of the comparisons, the things that are similar, things that are different between parallel fluxes and parallel streams. And if you click on the link at the bottom of the slide, it will take you to that description, which does a nice job of explaining how they compare and contrast. So that's the end of the overview of the three key classes in the Project Reactor API: Mono, Flux, and ParallelFlux.